Imagine a voice so ancient that it speaks not in words, but in vibrations rippling across the void. No sound touches your ears, yet the universe resounds. You are lying beneath a canopy of stars, still and silent. But overhead, reality is anything but quiet. The night sky is an active symphony, bursting with stories that traverse billions of years. It is the place where time stretches, where gravity bends, and where light becomes a messenger from forgotten epochs. Every photon from a distant star is a time traveler. When it touches your eye, you are not seeing that star as it is, but as it was 10, 100, a billion years ago. Starlight does not merely illuminate, it testifies. What you see is a fossil record in the medium of light. Yet the universe's most haunting music doesn't ride on sound waves. In the vacuum of space, traditional sound cannot travel, but the cosmos still sings. It sings in electromagnetic radiation, in gamma rays, X-rays, ultraviolet and radio waves. These signals, translated by radio telescopes, tell us of spinning neutron stars, the collapse of suns, and the faint hum of the infant universe itself. You are in the control room now. Massive radio dishes point to the sky. On the monitors, rhythmic pulses appear. These are pulsars, neutron stars spinning hundreds of times per second, each one the collapsed core of a supernova. They emit radiation with such perfect timing that we use them to keep our atomic clocks in check. The death of a star becomes the heartbeat of our civilization's measurements. Then there are the irregular voices, bursts of radio waves from quasars, from the twisted space-time near black holes, from the explosive births and deaths of stars. Some are steady, others are frantic. Each tells of extreme gravity, magnetic storms, and matter behaving in ways we still struggle to model. One of the universe's oldest sounds is the cosmic microwave background, faint radiation emitted just 380,000 years after the Big Bang. It pervades the universe, a leftover glow from a time before stars, before galaxies, before elements as we know them. It is the cosmic echo of the universe becoming transparent for the first time. Listen closer. Hydrogen, the most abundant element, speaks too. When it flips its electron's spin, it emits radio waves at a very specific frequency. With this, we map galaxies. We see where stars are born. We trace spiral arms. Interstellar gas clouds are not silent. They tell us where new suns will blaze into being. And our own star, the sun, is a wild instrument. It flares, it storms, it disrupts satellites and sparks auroras. It sends out coronal mass ejections, billion-ton clouds of plasma that can knock out power grids. It hums with activity beneath its surface, vibrating in oscillation modes we can detect. None of this is chaos. It is symphony. Patterns within patterns. Harmonies buried in noise. Chaos becomes data. Data becomes meaning. And yet, among all these signals, we hear whispers of something more enigmatic, something we cannot see but whose influence is overwhelming. Galaxies spin faster than they should. Light bends more than expected. A hidden force holds galaxies together. We call it dark matter. Dark matter is not just an absence, it is a presence without visibility. It neither emits nor absorbs light, but it has mass. It has gravity. It shapes the universe. In the 1970s, Vera Rubin noticed stars orbiting galaxies too quickly. They should have been flung into space, but they weren't. Something invisible kept them bound. That something, dark matter, makes up about 27% of the universe. We only see the scaffolding it creates. Imagine a dance, with visible stars and gas swirling around a phantom partner. The dancers move to music we cannot hear, led by something that eludes all senses but gravity. We map this dark matter by observing how it bends light, a process called gravitational lensing. Light from distant galaxies is curved, magnified, and split by mass we cannot detect, as if space-time itself is a warped mirror. There are theories. WIMPs, weakly interacting massive particles, are one candidate. These particles might pass through your body by the billions every second, unnoticed. Or maybe it's axions, exotic low-mass particles. Or perhaps it's not particles at all, but tiny primordial black holes born in the earliest seconds after the Big Bang. Underground detectors wait in stillness. They sit deep in old mines or under mountains, shielded from cosmic rays. waiting for a single particle of dark matter to collide with a nucleus and leave a trace. So far, silence. But silence in science is not failure. It is patience. It is readiness. It is knowing that absence can speak. The search continues. Each non-detection is a refinement, a narrowed path through the thickets of theory. And above, the stars go on spinning. Galaxies keep their form. The unseen hand persists, as if space itself remembers a shape we cannot yet recognize. Meanwhile, we move toward the most extreme place known to physics, the black hole. Born from the death of massive stars, black holes are regions of such density that space-time caves in on itself. A singularity lies at their core: infinite density. Zero volume. Around this point is the event horizon, the boundary beyond which nothing returns. Time behaves strangely near a black hole. To an outside observer, anything falling in seems to slow, to freeze. But for the falling object, time ticks as usual. Cross the event horizon, and all paths lead inward. Some black holes are stellar mass, formed from collapsed stars. Others are giants, millions to billions of solar masses lurking at the centers of galaxies. Sagittarius A, the supermassive black hole at the heart of the Milky Way, anchors our galaxy. Our solar system orbits it every 230 million years. In 2019, we saw the silhouette of a black hole for the first time. Not directly, but by imaging its glowing accretion disk matter spiraling in, heating to billions of degrees. The Event Horizon Telescope, a global array of radio observatories, gave us a picture of the M87 black hole, a bright ring around a shadow. And black holes do not live forever. Stephen Hawking predicted they emit faint radiation. Hawking radiation due to quantum effects. Over immense timescales, they will evaporate. The cosmos will grow dimmer, quieter. But not yet. Not today. For now, the universe still roars, even in its darkest corners. The distant moon hung low over the Martian horizon, a pale sliver against the rust-red dust. As the first explorers set their instruments in the soil, here, at the boundary of Earth's influence, a new perspective began to form. Beneath the planet's thin sky, stripped of a protective magnetosphere, the silence was not just auditory, it was existential. This was not Earth extended. It was something else, something wholly alien. The dust underfoot had not shifted for millions of years. Each grain was a relic, untouched by rain or running water, shaped only by the breath of thin winds and ancient impacts. And yet, in this stillness, a new kind of motion was born, not of rock or weather, but of thought. What would it mean to build a human presence on Mars? Could our minds, wired for forests and oceans, adapt to crimson plains and twin moons? The cosmos is not built to accommodate human need, but neither is it hostile in any deliberate way. It is indifferent, and in that indifference, there is a peculiar freedom. Mars, though often imagined as a dry, frozen desert, tells a richer tale. Evidence of past rivers, of ancient lakes, even of possible oceans, lies in the sinuous channels etched into its surface. Clay deposits, which only form in the presence of water, whisper of epochs when Mars was blue. And if it once held water, could it have once held life? The question is not trivial. It pushes against the boundaries of biology. Life, we now know, can exist in boiling sulfur springs, in the vacuum of space, in clouds of acid. Why not in the subterranean aquifers of an ancient Mars? To search for life is to search for connection, not merely in the microbial sense, but in the recognition that we are not a singular cosmic accident. If life emerged independently on Mars, even once, it would mean the universe is fundamentally inclined toward complexity, toward pattern, toward awareness. From orbit, Mars reveals scars of cataclysm volcanoes like Olympus Mons, the tallest in the solar system, and Valles Marineris, a canyon system that dwarfs Earth's Grand Canyon. These formations speak of forces vast and violent. They also remind us that Mars is not dead. It slumbers. Seismic activity and strange methane emissions hint at processes still ongoing beneath its crust. Perhaps it is not a world frozen in time, but one caught mid-transition. The journey beyond Mars takes us into realms of scale that bend comprehension. Past the asteroid belt, where Ceres, a dwarf planet, lurks as a forgotten embryo of planetary formation, we enter the realm of the gas giants. Jupiter, with its churning bands of storm and radiation belts, guards the solar system like a gatekeeper. Its gravity shapes the orbits of comets, shepherds asteroids, and may have shielded Earth from countless impacts. Yet it is not just a protector. Within its orbiting moons lie some of the most promising places to search for life beyond Earth. Europa, with its cracked icy shell, likely hides a liquid ocean beneath, warmed by tidal flexing. Ganymede, the largest moon in the solar system, possesses a magnetic field and anomaly among moons and hints at subsurface oceans of its own. Saturn's Enceladus ejects plumes of salty water and organic molecules from geysers near its south pole. These are not dead rocks. They are worlds in waiting. Each of these icy bodies challenges our terrestrial assumptions. On Earth, life clings to thermal vents on the ocean floor, independent of sunlight. Might similar ecosystems thrive in the dark seas of Europa or Enceladus? If so, the universe might teem with biology not in Earth-like temperate zones, but beneath frozen shells, in the warmth of tidal embrace. Uranus and Neptune, the ice giants, bring new mysteries. Their atmospheres swirl with exotic chemistry, and their magnetic fields tilt wildly from their rotational axes. Neptune's moon. Triton orbits backward, a clue to its captured origin, and geysers of nitrogen vent from its crust. These outer worlds are not merely far, they are strange in ways that challenge both instruments and imagination. Beyond them lies the Kuiper Belt, a realm of frozen remnants, including Pluto, whose demotion from planetary status obscures its intricate geology and possible internal ocean. The New Horizons mission revealed a heart-shaped basin of nitrogen ice and mountains of water rock. Even here, at the edge of sunlight, geology speaks. And then, at last, the heliopause, the boundary where the solar wind yields to the interstellar medium. Voyager 1 crossed it in 2012, becoming the first human-made object to enter interstellar space. Its golden record, bearing music and messages from Earth, floats onward into the dark. A whisper of sentience hurled into the abyss. What does it mean to extend our senses so far? To know, with certainty, that we have sent artifacts and perhaps soon, people beyond the nursery of Earth. It is not conquest, it is communion. The search for alignment with forces larger than ourselves. The impulse is not to dominate, but to understand. In the silence beyond planets, where only photons and particles drift, our thoughts continue. About time, about death, about continuity. When we plant a flag or a sensor, it is not to say we own this, but to declare we noticed. It is a profoundly humble act. The solar system is a cathedral of time and physics. Each moon, each orbit, each cratered surface is a chapter in a book older than humanity. And we, with our instruments and questions and dreams, are its youngest readers. But beyond reading, we may someday write, leave traces not only of biology, but of poetry, logic, compassion, a lander's medal, a rover's track, a human footprint pressed into Martian soil, not noise, but meaning. In the faint light of a distant sun, the first greenhouse might bloom, the first cry might echo in a dome, not as colonizers, but as participants in a story that is still being told. Imagine drifting through the frozen edge of our solar system, past the orbits of Neptune and Pluto, into the Kuiper Belt, where icy relics from the birth of the sun still orbit in their ancient paths. Here lie the dwarf planets, comets, and countless icy rocks that whisper of a primordial time. It is a silent realm, barely touched by sunlight, where time seems to stretch and celestial mechanics dance in slow motion. As you pass through, your gaze is drawn toward the mysterious Oort cloud, a hypothetical shell of icy objects far beyond the planets, stretching halfway to the nearest stars. If a comet begins its long journey toward the sun, it may have originated here, perturbed by the gravity of a passing star or a ripple in the galactic tide. The outermost reaches of our solar system mark the boundary between the known and the speculative. This is where gravitational dominion gives way to interstellar drift. Out here, the solar wind fades, and the heliopause, our sun's final breath, meets the interstellar medium. Beyond this invisible threshold lies the vast ocean of the galaxy, populated by rogue planets, errant comets, and the interstellar gas from which stars are born. Each particle of dust out here is a relic older than any terrestrial stone, untouched since the galaxy's youth. Our journey now moves inward, not in space, but in scale. We dive beneath the surface of understanding, into the infinitesimal heart of matter. Everything you see, touch, and know is made of atoms, billions of them dancing in patterns too small to perceive. Each atom contains a nucleus, a dense core of protons and neutrons, surrounded by a ghostly cloud of electrons. But even these subatomic particles are not fundamental. Inside protons and neutrons reside quarks, held together by gluons in a dynamic tension described by quantum chromodynamics. Quarks, electrons, neutrinos. These are the building blocks of the universe, governed by the rules of the standard model of particle physics. It is our most successful framework for understanding matter and its interactions. Yet, it is also incomplete. It says nothing of gravity, of dark matter, or of the strange imbalance between matter and antimatter. Physicists search for unification, a deeper layer of reality where all forces merge, where the universe writes its rules in simpler terms. To probe this hidden structure, scientists use colossal machines, particle accelerators like the Large Hadron Collider. These vast rings hurl particles to near light speed and smash them together, recreating conditions just moments after the Big Bang. From the debris of these collisions, we discovered the Higgs boson, a particle that gives mass to others through a field that permeates all of space. It is like an invisible molasses through which everything must pass. But even the Higgs, profound as it is, does not answer every question. What stabilizes the mass of the Higgs itself? Could supersymmetry provide the answer, positing partner particles for every known one? Or might string theory hold the key, suggesting that all particles are different vibrations of tiny strings existing in 10 or 11 dimensions? These ideas remain unproven, beautiful, but elusive. The closer we look, the more the universe begins to resemble a question. Is space-time itself granular, made of discrete units smaller than any atom? Some physicists believe in loop quantum gravity, a model where space and time emerge from networks of interconnections, quantum threads woven into the cosmos. Others ponder the holographic principle, which suggests that everything we experience in 3 dimensions is encoded on a distant 2-dimensional surface, like a cosmic projection. And what of time? Is it an arrow, always pointing forward, or an illusion born from entropy? The laws of physics are mostly time-symmetric. They work just as well in reverse. Yet, our experience of time is not symmetric. We remember the past, not the future. Entropy, the measure of disorder, increases. This is the one true direction time seems to follow. But why did the universe begin in a state of such low entropy? Why was it so ordered at its birth? Perhaps the most profound mysteries lie not in the stars, but in the silent intervals between them, in the gaps of our knowledge, in the stillness where science meets philosophy. The cosmos is not just a place of planets and particles. It is a stage where meaning, consciousness, and curiosity come to life. We, the observers, are also part of the experiment. As we float back from the microscopic into the vastness again, we carry with us the recognition that we are not separate from the universe, we are of it. Each atom in your body was forged in the heart of a star. Each breath echoes cycles of carbon and oxygen that have danced through 1,000 forms. The universe dreams through us, and in contemplating it, we allow it to know itself. The edge of the solar system, the edge of matter, the edge of certainty. These are not limits, but invitations, reminders that exploration begins when we dare to ask the questions that have no easy answers. 100,000 light-years from end to end. The Milky Way is a structure vast enough to contain billions of stories, and yet it is only one galaxy among countless others. Its spiral arms hold a history of cosmic birth, violence, and evolution. But even in its grand design, our vantage point remains constrained. We look from the inside out, our solar system nestled in one quiet fold of the Orion Arm, orbiting the galactic center like a boat gently circling the eye of a storm. The stars above seem eternal, yet they too move, pulled by invisible currents, sculpted by forces we cannot touch. Each one participates in a vast celestial choreography, It takes the Sun 230 million years to complete just one galactic orbit. In that time, entire species have risen and vanished on Earth. The dinosaurs lived and died without completing a single cosmic lap. Now, under the night sky, we follow their path with radio telescopes and digital star charts. Beyond the spiral arms lie stellar halos and globular clusters, ancient, spherical groupings of stars orbiting the galaxy like bees around a hive. These clusters are fossils, containing stars almost as old as the universe itself. Studying them is like peering into a cosmic archive, unlocking information about the galaxy's adolescence. Their orbits are wild and elliptical, often slicing through the galactic disk. Their presence hints at collisions, past galactic mergers that left behind structural echoes. We now know the Milky Way is on a slow, inevitable collision course with the Andromeda Galaxy. In roughly 4.5 billion years, the two spirals will begin to interact. Their stars will mostly pass without colliding, like dust motes blown through one another. But gravity will stretch and warp the galaxies into streamers of stars. The final product will be an elliptical galaxy, swollen and slow. Some call it Milkomeda. It will be a new home for old stars. But galaxies aren't just stellar cities. They are governed by dark matter halos invisible, massive envelopes that dictate the galaxy's structure and motion. These halos are not decorative. They are architectural. Without them, spiral arms would fly apart. The visible galaxy is just the skin of a much deeper, invisible anatomy. Within this scaffolding, gravity sculpts matter into patterns and forms that are replicated across the cosmos. These structures form filaments, walls, and voids the cosmic web. On the grandest scale, the universe resembles a neural network, with galaxies as nodes connected by filaments of dark matter and gas. Between these filaments lie immense voids, where few galaxies dwell. These are the deserts of the cosmos, vast stretches of near-nothingness. If you could step back far enough to see the web in full, you might feel as if you were gazing at a living organism. Yet this structure is dynamic. Superclusters slowly drift, galaxy clusters merge, and quasars, supermassive black holes at galactic cores, send jets of particles through intergalactic space. These active galactic nuclei are among the brightest phenomena in the universe. They burn with energy drawn from the innermost orbits of matter, spiraling toward gravitational oblivion. Their light travels billions of years to reach us, a testament to power born from collapse. Instruments like the James Webb Space Telescope now peer into these deep structures, capturing light from the earliest galaxies. It sees not just the glow of stars, but the spectral fingerprints of their composition: oxygen, carbon, even water vapor in nascent planetary systems. We are watching the universe watch itself become. In this light, we begin to glimpse not only what the cosmos is, but what it has the potential to be. As we trace these immense structures, the arrow of time continues its slow cosmic march. Thermodynamics tells us that entropy increases, order becomes disorder. Galaxies will eventually run out of fuel, their stars dimming, their matter decaying. But the story doesn't end with extinction. Matter that once formed stars and life will disperse, contributing to new structures. Nothing is wasted in the cosmos, everything transforms. On some distant day, when the last star flickers out and black holes begin their long evaporation via Hawking radiation, the universe may reach a state of maximum entropy, a diffuse, dark sea of particles and fading remnants. But even then, the laws of physics persist, whispering through silence. The universe remembers its origins not in memory, but in structure. And yet, across this vastness, the spark of inquiry continues. From a small blue planet on the edge of a minor spiral arm, consciousness has risen that dares to ask where it came from and what might lie ahead. We are not mere observers. We are participants in a universe still in the act of becoming. The Earth rotates slowly beneath a sky full of secrets, and as dawn begins to stain the horizon with soft light, the final frontier we've been tracing reveals yet another boundary, not of matter, nor of space, but of understanding itself. Human cognition, our curiosity, our fears, our models is the last telescope we aim outward and inward. In the midst of distant galaxies and decaying stars, the very idea of intelligence demands attention. Intelligence is not just a feature of biology, it may be an emergent property of matter, given time, complexity, and the right constraints. Earth may be a proof of concept, but if minds can emerge here, why not elsewhere? Could galaxies be learning systems? Could consciousness, somehow, be entangled with cosmology itself? We usually think of intelligence as a late evolutionary development, a tool for navigation, tool-making, storytelling. But consider the possibility that intelligence is also a cosmic phenomenon, an entropy negotiator, a meaning maker in an otherwise indifferent expanse. Some physicists speculate that life, and perhaps intelligence, could serve as a counterbalance to entropy, shaping order even as the universe trends toward thermal equilibrium. In this framework, every self-aware being becomes a node of resistance, a flicker of coherence against the pull of chaos. And every question we ask about the universe is the universe, in a sense, asking itself. Now imagine a future where intelligence becomes not just biological but cosmic in scale. Civilizations, if they survive their infancy, may begin reshaping not just planets, but stars. Dyson spheres, hypothetical megastructures encasing stars to capture their full energy output, are one example. We haven't detected any yet, but our searches for Type 2 civilizations, those capable of harvesting the energy of entire stars, or Type 3 civilizations that manipulate galaxies, continue. If they exist, they're subtle, or they've transcended detectable physicality altogether. Perhaps intelligence eventually merges with space-time structure, embedding itself as information gradients, quantum echoes, gravitational imprints. And if civilizations collapse as ours might, they still leave behind artifacts of thought, radio waves sent eons ago, gravitational lensing patterns from abandoned stellar engines, the final memory of a thinking species encoded in the rotation of a neutron star. But even if we are alone uniquely aware in an otherwise quiet cosmos, our awareness may be enough. To observe the universe is to become part of its unfolding. Just as measurement changes the state of a quantum system, consciousness alters the narrative trajectory of the cosmos. And what of the end? What awaits when the stars burn out, when black holes evaporate, when entropy finishes its slow, patient erasure? The far future of the universe is an austere place, cold, dark, sparse, but some speculate that information might never be entirely lost. The universe, even in its final state, could remain a container of memory. Through theories like the holographic principle, where the three-dimensional world is described by two-dimensional information at its boundary, we begin to glimpse a reality where space, time, and matter are all emergent properties of deeper informational structures. Some go further still, proposing that the universe itself is a kind of computation, not metaphorically, but literally a quantum process unfolding across dimensions. From this perspective, our thoughts, our dreams, our efforts to understand the stars are operations in a grander algorithm whose purpose we may never decode. Still, we calculate, we remember, we imagine. And imagination is no small thing. It is the propulsion of science, the architecture of empathy, the poetry of discovery. Through imagination, we transcend the here and now, projecting ourselves into alien atmospheres, lost epochs, and speculative futures. As we continue this cosmic journey, we must also face the mirror. The tools of astronomy, cosmology, and particle physics have given us unprecedented power but also deep responsibility. What we do with this knowledge will shape not just our destiny, but the future of sentient matter in this corner of the universe. How we handle climate instability, resource depletion, artificial intelligence, and our interdependence with ecosystems will determine if we're a long-lived civilization or a brief spark in galactic time. The stars will go on, but whether we remain to witness them is not guaranteed. Even the act of looking up, so simple, so ancient, is a form of hope. It says, there is more than this moment. There is more than ourselves. It acknowledges both our fragility and our vast potential, and it affirms that wonder is still the most honest response to existence. So, when you next lie beneath the open sky, remember you are a participant in the most complex, most beautiful, most mysterious story ever told. A story still being written, a journey still unfolding. And the stars. They are not just lights in the sky. They are questions, waiting for minds to ask them.
The sky above Babylon was not yet myth nor yet science, but a canvas of meanings, precise and sacred, on clay tablets, marked by reeds under oil lamps. Priest astronomers sketched the movements of stars and planets. 4,000 years ago, they divided the heavens into 12 constellations, the zodiac through which the sun, moon, and planets wandered. They mapped Venus's appearances and disappearances, timed eclipses, and predicted the cycles of the moon. Their sky was not inert, it was divine, encoded with the intentions of gods. Yet it wasn't purely faith. These early sky-gazers mastered arithmetic, compiled multiplication tables, and developed a rudimentary form of computational astronomy. They understood patterns well enough to forecast solstices and seasonal changes. In their cosmology, precision lived alongside prayer. This fusion of myth and measurement would echo for millennia. In ancient Mesopotamia, watching the heavens meant listening to the will of the gods. But in a distant land across the Aegean, a different kind of question was beginning to form, not what the gods willed, but what the world was made of. On the coast of Ionia, in the city of Miletus, Thales peered into the nature of reality and saw not gods, but water. It was, he proposed, the primal substance from which all else derived. Soon others followed. Anaximenes suggested air, Heraclitus chose fire, and Empedocles added earth, along with the mysterious ether. These were not wild guesses, but early attempts to reduce the complexity of nature to foundational elements, elements that behaved predictably, combined mechanically, and obeyed conservation. With them, a new kind of logic entered the world. These thinkers did not merely observe the world, they abstracted it. Like blacksmiths explaining flame and forge, they used metaphors from their craft. Clay becomes pottery, ores become metal. In this transformation, they found analogies for nature itself. What changes may do so without divine intervention? Change could be understood through interactions, not intentions. By the 6th century BCE, a revolution had begun, not of politics, but of inquiry. Pythagoras, a mystic of mathematics, reimagined the cosmos as a geometrical harmony. To him, number wasn't mere quantity, it was essence. The earth, he said, was a sphere, and the heavens sang inaudible music as the celestial spheres rotated in perfect circles around a central flame. These harmonies, real but unreachable to human ears, mirrored the mathematical beauty he saw in triangles and ratios. The physical and metaphysical were entwined. Where Babylon charted, Greece questioned. Heraclitus, the weeping philosopher, saw a cosmos of fire and flux. Everything flows, he said. Nothing stands still. To him, conflict was not destruction, but the very engine of existence. Wisdom was knowing how things change. Parmenides, in reply, argued the opposite: nothing changes, and change itself is illusion. Being is one, continuous, undivided. His truth was abstract, his universe serene. The apparent world the flicker of leaves. The rising sun was, to him, a deception of the senses. His ideas, strange at first glance, foreshadowed modern physics, where Heraclitus hinted at Newton's dynamic cosmos. Parmenides gestured toward Einstein's space-time block, where all events coexist in a timeless geometry. Here begins the ancient tension that will shape all cosmology, between permanence and change, between unity and multiplicity. And then came Socrates. Unlike the natural philosophers before him, he turned the gaze inward. Why, he asked, do we care how atoms behave if we do not understand why we exist? For him, understanding required moral clarity. The soul, he said, was immortal, and knowledge of the world meant nothing without knowledge of the self. He asked why the stars shine, but not in terms of heat or fusion, but of purpose. His questions ignited a flame in his student, Plato. Plato took Pythagorean harmony and Socratic ethics and forged a universe of duality. The world we see, he said, is shadow a cave wall upon which the light of truth casts images. Reality lies beyond the senses, in perfect forms, justice, truth, beauty, eternal and unchanging. The visible stars are mere echoes of their invisible perfection. He imagined the cosmos as a sphere, a perfect divine shape animated not by randomness but by mind. In Plato's vision, the intellect transcends chaos and imposes order. This Platonic impulse to seek hidden symmetry beneath apparent disorder still fuels modern physics. Three visions took hold in the ancient world: Aristotle's structured universe, Epicurus's atomistic cosmos, and Zeno's fated order. Aristotle's cosmos was layered in local earth at the center, wrapped by crystalline spheres of ether, each bearing the moon, sun, and planets, culminating in the stars. Change happened below the moon. Above perfection, the heavens rotated in endless circles, for circles were divine. In his view, all things sought their natural place. Earth fell, fire rose, the ether revolved, motion required cause, and vacuums impossible. He denied atoms, for they implied empty space. Yet in doing so, he preserved the logic of place and purpose. Everything moved toward rest, toward its rightful place in a cosmic hierarchy. This order, though rigid, comforted. Epicurus saw the opposite: no central earth, no purpose, no gods guiding the stars. Atoms, he said, swirl through the void, infinite in number, eternally colliding and combining. Worlds are born, dissolve, and reform endlessly. The soul itself is atomic when the body dies. It dissolves. Death is not to be feared. Ethics, for him, meant living simply, avoiding pain, cultivating friendship. His cosmos was indifferent but free. As Zeno of Citium, the Stoic, stood between. To him, the universe was alive, a single, rational organism pervaded by divine reason, or logos. Stars were living embers, and the cosmos pulsed in cycles of birth and destruction. Fate was real, but virtue lay in accepting it. The Stoics prized duty, temperance, and wisdom. Their cosmos was finite but meaningful, ordered yet vulnerable to catastrophe. 2,000 years later, their vision would inspire the Victorian model of a finite cosmos in an infinite void. These ancient visions, geometric, atomic, ethical, were not competing sciences, but cosmologies, stories that made the world intelligible. They offered not just explanations but orientations. And while they disagreed on substance, they agreed on one thing: the universe was intelligible. This belief, radical, even defiant, would be tested in centuries to come, but it would never quite disappear. After centuries of speculation, analogy, and metaphysical mapping, the cosmos began to take shape not just in the mind but in mechanisms. In Athens, the question of planetary motion that had vexed the students of Plato found a new formulation. What are the uniform and ordered movements of the planets? Why do Mars and Jupiter trace strange loops across the sky? Eudoxus, a student of Plato, imagined the heavens as a nested arrangement of spheres, concentric and rotating, each bearing a planet, each turning on its own axis. The outermost sphere moved the stars. Beneath it, layers of crystal carried the wanderers. It was the first attempt to build a mechanical cosmos. But these were still analogies, mathematical metaphors for divine movement. Then came Aristotle, who took these spheres and gave them mass, motion, and substance. To Aristotle, nature was a system with purpose. The earth, heavy and still, sat at the center. Around it, the moon, the planets, and the stars circled in layers of translucent ether. Each sphere required motion, each motion required a cause. Up to 56 spheres were needed to account for the irregularities in planetary motion. His cosmos was not infinite. It was bounded, finite, enclosed by the outermost sphere of fixed stars. Beyond that, nothing. No space, no time, no being. Infinity, he argued, was not just absurd, it was impossible. The perfect circle was the path of the heavens, the straight line, flawed and earthly. In Aristotle's physics, everything moved to its natural place. Earth and water fell, fire and air rose, ether revolved, and in the sublunar world, the domain of change and decay, motion required force. Without a mover, nothing moved. Thus, the heavens were moved by divine, unchanging thought, the unmoved mover, pure actuality. Yet Aristotle's system had a flaw. It could not explain the strange retrograde motions of the planets, their apparent looping reversals in the night sky. Nor could it account for their variable brightness. Greek astronomers responded with complexity. They introduced eccentric circles, whose centers were offset from Earth, then epicycles, circles upon circles, small orbits superimposed on larger ones, and finally, equants, a mathematical trick where a planet moved at a uniform speed but around a point not centered on Earth. It was an increasingly elaborate clockwork. In Alexandria, in the 2nd century CE, the mathematician Claudius Ptolemy synthesized centuries of models into a grand geometric engine. His book, the Almagest, became the definitive account of the heavens for 1400 years. With careful tables and algorithms, Ptolemy's system could predict eclipses, solstices, and planetary positions with remarkable precision. But it was also cumbersome, a palace of nested gears built on flawed foundations. Beneath it all, a quiet revolution still lingered. Back in the 5th century BCE, in Abdera, the philosopher Democritus had imagined a very different cosmos, one without purpose, one without spheres, a void, infinite in extent. Within it, countless indivisible particles, atoms danced, collided, combined, and fell apart. The world, he said, was not made by gods or guided by reason, but by chance and necessity. Everything, from stars to souls, was made of atoms and void. His teacher, Leucippus, had laid down the first law of causality. Nothing occurs at random, but everything happens out of reason and necessity. It was the earliest expression of determinism in the West. Yet this radical atomism was rejected by Plato, ignored by Aristotle, and forgotten by most of antiquity. Only the Epicureans preserved it. Epicurus, in the 4th century BCE, revived the atomists' ideas. He added ethics to physics. If the universe is made of atoms, and the soul dissolves at death, then there is nothing to fear. The gods exist, perhaps, but they do not intervene. The highest good is not indulgence, but peace, freedom from fear, pain, and superstition. His school admitted women, celebrated equality, and taught that friendship, not faith, is the foundation of happiness. His follower, Lucretius, would later distill these ideas into poetry. The Nature of the Universe, written in the 1st century BCE, is a hymn to natural law and material order. But this vision, secular, sensual, serene, was dangerous. As Christianity rose, Epicureanism fell. A universe without divine purpose was heresy. The atomists were silenced, their works buried, their names condemned. Aristotle, with his teleology and layered heavens, became the preferred cosmologist of Christendom. And so, through late antiquity and into the Middle Ages, the Aristotelian universe reigned, a sphere of spheres, finite and ordered, crowned by the prime mover and sanctified by Scripture. Earth was not just central, it was the axis of divine intention. Heaven lay above, hell below. The universe was a moral landscape as much as a physical one. But cracks were forming. As Europe slept through the early medieval centuries, Islamic scholars in Damascus, Baghdad, and Cordoba preserved and extended the knowledge of the Greeks. They translated Aristotle, refined Ptolemy, questioned Galen, and improved upon Indian and Persian mathematics. By the 9th century, they had re-established the spherical Earth, embraced astronomy as science, and begun rethinking the structure of the cosmos. From their manuscripts, knowledge re-entered Europe like sunlight through broken shutters. In the 13th century, the universities of Paris and Oxford were born. Scholars like Thomas Aquinas labored to reconcile Aristotle with Christianity. They preserved his physics, but modified his metaphysics. God, not the prime mover, ruled the universe, yet still Earth remained at the center. Not everyone agreed. Roger Bacon, a Franciscan monk, called for a return to observation, mathematics, and experimentation. He saw that true knowledge came not from books, but from the world itself. In doing so, he pointed toward the future. The Aristotelian universe with its spheres, perfections, and celestial stability was nearing its end. Soon, a Polish cleric would open a book, look to the heavens, and wonder, what if Earth is not the center? What if it moves? The year was 1543. In a quiet corner of Europe, far from the universities of Paris or the courts of Rome, an aging Polish canon named Nicholas Copernicus released a book that would unmake the heavens. De Revolutionibus Orbium Coelestium. On the revolutions of the celestial spheres was not a declaration, but a proposition. A modest idea that the Earth rotates on its axis and revolves around the Sun, that the Sun, not the Earth, is the fixed point about which the planets circle, that the heavens are not fixed in place, but in motion, measured not by divine spheres, but by celestial mechanics. It was a quiet book, and it made a quiet sound, but the world would never be the same. Copernicus had studied Ptolemy's epicycles and found them ungainly. The equants those mathematical cheats offended his Platonic sense of elegance. He knew of earlier hints, Philolaus, Aristarchus, and the heliocentric whispers that had never quite died. Copernicus sought to restore harmony, not incite rebellion. He kept the perfect circles, but shifted the frame. By placing the sun at the center, he reduced the need for cosmic acrobatics. Retrograde motion, the strange backward loops of the planets became an illusion, explained by perspective and parallax. But the shift was more than geometrical. It was ontological. If Earth moves, then Earth is not the center of the universe. If it moves, it is like the planets, one among many. And if Earth is not central, then neither are we. The Copernican model did not immediately convince. It still relied on circles and failed to match the predictive precision of Ptolemy's ancient tables. Worse, it required the stars to be impossibly distant, so far away that no parallax could be seen. To many, this was absurd. But to Thomas Digges, an English astronomer writing in 1576, it was a revelation. He took Copernicus's finite model and tore away the outer shell. The sphere of stars, he argued, was not a shell at all, but an infinite ocean of suns. The universe, he said, extended without edge, without limit. The stars were not fixed points, but other worlds, scattered through boundless space. It was the first time in history that infinity entered cosmology not as a fear, but as a feature. And in London, a monk named Giordano Bruno read Digges's words and was set ablaze. Bruno embraced the infinite not as a challenge, but as a liberation. The universe, he proclaimed, has no center, no circumference. The stars are suns, the planets are countless. Life is not a miracle of Earth, but the law of the cosmos. In this boundless expanse, God is not diminished, but magnified. The excellence of God, he wrote, is shown not in one sun, but in infinite suns, not in one world, but in infinite worlds. For these ideas, for his refusal to place creation in chains, Bruno was imprisoned, tortured, and burned at the stake in Rome in 1600. But his fire did not die. That same year, a Danish nobleman named Tycho Brahe peered at the heavens from his observatory on the island of Haven. With instruments of astonishing precision, he charted the planets with naked-eye accuracy unmatched in his time. He rejected Copernicus, not out of dogma, but out of observation. If Earth moves, he argued, the stars must shift slightly as Earth moves parallax, but none was seen. He did not know that the stars were unimaginably farther than even Digges imagined. So he proposed a compromise. The planets orbit the sun, but the sun orbits Earth. It was a hybrid model, mathematically rich, philosophically cautious, and it preserved the Earth's centrality, for now. After Tycho's death, his assistant inherited not only his data, but his mission. Johannes Kepler, a sickly, visionary mathematician, worked through Tycho's numbers with relentless passion. For years, he struggled with Mars. Its orbit refused to fit perfect circles. At last, he broke with tradition. The orbits, he discovered, were not circles but ellipses. The planets move faster when closer to the sun, slower when farther, and they sweep out equal areas in equal times. Kepler had found the true geometry of the heavens. 3 laws, precise and elegant, laid the foundation for modern celestial mechanics. But he was no dry geometer. To Kepler, the cosmos was music, the harmony of spheres not abandoned, but transfigured. In his mind, the planets sang inaudible chords as they traced their ellipses. The universe, he believed, was the image of God, not static, but dynamic, intelligible, divine. Yet few understood him. Then in Pisa, a man built a telescope and turned it skyward. Galilei, bold, brilliant, and irreverent, saw mountains on the moon, moons orbiting Jupiter, and stars without number in the Milky Way. He shattered the Aristotelian heavens. No longer could the skies be perfect and unchanging. They were material, dynamic, like Earth. He championed Copernicus, scorned Ptolemy, and mocked the old scholastics. Nature, he said, is written in the language of mathematics, and to read it, we must observe, measure, and calculate. And his books, like The Starry Messenger and Dialogue Concerning the Two Chief World Systems, ignited controversy. The telescope did not just enlarge the sky, it exposed dogma. In 1633, under threat of torture, Galileo recanted his heliocentrism, and yet he is rumored to have whispered, "It moves." The Earth moved, the heavens shifted, and the center could no longer hold. Even as Galileo recanted, the Earth kept moving. The sun still burned at the center of its planetary retinue, and quietly, in the northern countryside of England, a child was born in the year Galileo died. His name was Isaac Newton. He would inherit the cosmos that Copernicus proposed, that Kepler clarified, that Galileo defended, but he would give it something no one else had: an engine. Before Newton, the heavens were still somewhat separate. Celestial bodies followed rules, circular or elliptical, perhaps, but earthly things obeyed others. An apple falls, a moon arcs. But what connects the falling fruit to the orbiting moon? Gravity. In a single, sweeping synthesis, Newton answered the ancient question of why things move. With his Philosophia Naturalis Principia Mathematica, published in 1687, he united the earth and sky in a single framework. Force and mass, acceleration and inertia, governed all things everywhere, always. No need for angels to push the planets, no divine hands to spin the spheres, just the laws of motion and the invisible pull of gravity and attraction that reached across emptiness, instantaneously, from star to star. In Newton's cosmos, the universe became a vast clockwork, a divine mechanism ticking with perfect predictability. Time and space were absolute, the backdrop against which the dance of bodies unfolded. It was elegant, it was terrifying, for in its perfection, it left no place for spontaneity, or mystery, or even God, except perhaps as the initial clockmaker. The deity of Newton's universe did not intervene. He designed, wound, and stepped back. But still, The question lingered, what was this space? This void through which gravity acted? The ancient Greeks had denied the void. Aristotle declared it impossible. But by the 17th century, the void returned with force. Space was not nothing, but a stage, an infinite expanse, measurable, empty, and real. For the Epicureans, this was vindication. Their atomistic void, long suppressed, was reborn in Newtonian physics. The universe, once again, was infinite in extent and governed by impersonal law. And yet others resisted. In France, philosophers like Descartes still imagined a plenum, a universe filled with subtle matter, vortices spinning the planets. In the Church, the idea of infinite space threatened the uniqueness of creation. If there were infinite worlds, did each have its Christ? Was humanity still the center of divine concern? Theologians searched for ways to reconcile Newton's laws with Scripture. Some succeeded, crafting a natural theology in which the perfection of the laws proved the wisdom of God. Others recoiled, fearing a mechanized cosmos that left no room for miracle. Meanwhile, new voices entered the conversation. Giordano Bruno had imagined infinite worlds. Now, thinkers like Edmund Halley began to catalog stars, nebulae, and comets. Astronomy shifted from speculation to data. Telescopes grew longer, sharper. Maps of the heavens bloomed with detail. In England, the Royal Society promoted the motto nullius in verba, take nobody's word for it. Observation, not authority. Experiment, not dogma. This was a new cosmology not just of space, but of method. Bacon, Descartes, Newton, and Galileo had turned nature into a problem to be solved, not a mystery to be revered. Yet the heart still yearned. In poetry and painting, the universe remained sublime. William Blake saw angels in beams of light. Newton, to him, was not a prophet, but a tyrant, reducing the rainbow to a prism. May God us keep, he wrote, from single vision and Newton's sleep. For all its rigor, the mechanistic universe felt cold to many. Infinite space was liberating but also lonely. The celestial spheres no longer sang, the stars no longer watched, the heavens no longer cared. Still, the revolution continued. Philosophers debated the implications. If everything followed law, where was freedom? If the mind was made of matter, were thoughts also determined? Were we just machines, thinking, feeling, but ultimately predictable? Some, like Spinoza, embraced this. To him, God and nature were one. The universe was divine, not because it was guided, but because it simply was. Existence itself, infinite and necessary, was sacred. Others recoiled, seeking a return to purpose, to spirit. And so, cosmology fractured. On one side, the Enlightenment reason, empiricism, universality. On the other, romanticism feeling, mystery, the ineffable. Yet both shared a belief that the cosmos could be known. By the 18th century, star charts filled European libraries. Comets, once omens, were now celestial visitors with orbits. The solar system was mapped, its planets timed like gears. Light was dissected, gravitation confirmed, but questions remained. What lay beyond the stars? Was the universe infinite or finite, static or expanding? Was time eternal or born? Newton had no answer. He admitted the instability of his system. Gravity should collapse the stars into a point. Something was missing. Perhaps, he mused, divine intervention was still required not to move planets, but to reset the balance, now and then. A ghost in the machine. This was not the end of cosmology. It was a new beginning. At the turn of the 20th century, the Newtonian cosmos still reigned majestic, orderly, and immense, but its edges were beginning to blur. In the deep mathematics of James Clerk Maxwell, light was not just a wave in the ether, it was an electromagnetic phenomenon, rippling at a fixed speed. But that fixed speed raised a question: what was it relative to? Enter Albert Einstein. In 1905, a quiet patent clerk in Bern set the world on fire. With his theory of special relativity, he showed that space and time were not absolutes. They were woven together relative, elastic, and dependent on the observer. Time dilated, length contracted, mass increased. The Newtonian scaffolding trembled. A decade later, Einstein revealed his general theory of relativity. Gravity was no longer a force acting across empty space. It was geometry. Matter tells space how to curve. Curved space tells matter how to move. The sun doesn't pull the Earth, it bends the space-time around it. The Earth falls freely along this curvature, tracing an orbit not by force, but by geometry. With that, Einstein dethroned the last vestiges of Aristotle and Newton. The void became a fabric. The cosmos was dynamic, and it expanded. In 1929, Edwin Hubble peered through the great telescopes of Mount Wilson and found that galaxies were not static, they were fleeing. Their light stretched into red. The farther away, the faster they receded. The universe, it turned out, had a beginning. Suddenly, the ancient question, eternal or created, was back. The Big Bang model emerged: all matter, energy, space, and time erupting from a singularity. No before, only a beginning. The cosmos, once imagined as a stable stage, was now a firework. And yet, as relativity reached cosmic scales, quantum mechanics unraveled the microcosm. At the atomic level, the world became strange. Particles behaved like waves. Locations blurred into probabilities. Electrons didn't orbit, they existed as clouds of possibility. Heisenberg's uncertainty principle declared that precision was an illusion. The more you know a particle's position, the less you know its momentum. Reality was not fixed, but probabilistic. Worse, or perhaps more wondrous, observation itself became part of the equation. The act of measurement collapsed a wave function into a particle. The cosmos wasn't just out there, it responded. Some called this the return of the observer. Others feared the death of objectivity. Where Newton saw predictability, quantum theory revealed indeterminacy. Where Einstein saw curvature, quantum physicists saw superpositions. The two frameworks, relativity and quantum mechanics, worked perfectly in their domains, but together they clashed. One described the vast, the other, the minute. But at the center of a black hole, or at the beginning of the universe, both were needed, and no one had yet unified them. Into this tension stepped bold thinkers. Some proposed string theory, that particles are not points, but tiny vibrating loops. Others imagined multiverses, quantum foam, holographic principles. Space and time, once seen as a backdrop, became emergent like temperature, arising from deeper laws. Perhaps the universe is not built from particles, but from information. And yet, for all this mathematical elegance, mystery abides. Dark matter, invisible scaffolding, outweighing visible matter 5-1. Dark energy, a force pulling galaxies apart faster and faster, defying gravity. Together, they compose 95% of the cosmos. We do not know what they are. We live in a universe we barely understand, and yet, we can measure it, map it, model it. From Babylonian astrologers to quantum computers, the arc of inquiry stretches. We ask the same questions. What is the universe? Why does it exist? What is it made of? What is our place? Every cosmology is a story not just about the stars, but about ourselves. The Earth at the center, or nowhere special. The gods above, or the void within. A realm of fates, or a playground of chance. In every age, cosmology reflects our deepest assumptions about order, about purpose, about meaning. Today, some scientists speak of a final theory, a unified field, a theory of everything. Perhaps we will find it. Perhaps not. Perhaps the journey matters more than the destination. Like the stars, we too are patterns in motion, brief, brilliant, and self-aware. The universe, having taken form, now contemplates itself through us. And in that reflection, Fleeting as it may be, something eternal flickers.
14 billion years ago, everything that exists today was compressed into a point smaller than an atom and exploded outward faster than light itself. This is the story we tell ourselves, the foundation of our cosmic understanding. But what if we have it backwards? What if the Big Bang was not an explosion from nothing, but something far stranger? A white hole, spewing matter and energy from another universe entirely. We will journey through colliding dimensions, explore cosmic fountains that defy physics, and uncover evidence that our entire reality might be the exhaust from the universe next door. Prepare yourselves. We begin. We stand at the edge of the greatest mystery in science. The Big Bang Theory tells us that 13.8 billion years ago, all matter and energy in our universe emerged from a singularity, a point of infinite density where the laws of physics break down completely. But here lies the problem that has haunted cosmologists for decades. How does something come from absolutely nothing? The mathematics of general relativity work perfectly until that very first moment. Then, they collapse into nonsense. Temperature becomes infinite. Density becomes infinite. Time itself stops having meaning. Think of it like trying to divide by zero on a calculator. The screen just shows error. That is exactly what happens when we try to understand the first instant of our universe. Every equation that describes reality simply cannot handle the conditions at the Big Bang. We can trace the universe back to when it was 1 second old, 1 millisecond old, even 1 trillionth of a second old. But that final step to zero remains impossible. Scientists have proposed countless solutions. Maybe time itself began at the Big Bang. Maybe our universe is one bubble in an infinite foam of universes. Maybe quantum fluctuations in empty space created everything we see. But each of these explanations requires something to already exist: time, space, quantum fields, or the physical laws themselves. None of them truly explains creation from absolute nothingness. The singularity at the Big Bang shares an eerie similarity with another cosmic phenomenon that physicists understand even less. Black holes also contain singularities, points where matter collapses to infinite density and our equations fail. But Einstein's theory of relativity suggests something remarkable. Every black hole might have a mirror image, a theoretical object known as a white hole, which expels matter and energy instead of consuming it. While black holes trap everything behind an event horizon, a one-way membrane from which nothing can escape, white holes do the exact opposite. They explosively reject everything, making it impossible for matter or light to enter. If you could somehow approach a white hole, you would see it blazing with incredible energy, spewing matter outward at tremendous speeds. The resemblance to our universe's birth is impossible to ignore. Consider the evidence. Both the Big Bang and a white hole involve massive amounts of matter and energy appearing from a single point. Both create event horizons that separate the inside from the outside. Both involve singularities where our current understanding of physics breaks down. The Big Bang scattered matter and energy throughout space in all directions, exactly as a white hole would. Even the cosmic microwave background, the leftover heat from the early universe, matches what we would expect from the cooling remnants of a white hole that has been expanding for billions of years. But this raises an even more disturbing question. If our Big Bang was actually a white hole, where did all that matter and energy come from? The answer might lie in understanding what happens on the other side of the cosmic mirror. White holes exist in the mathematics of general relativity as the perfect temporal opposites to black holes. While a black hole is a region of space-time where matter falls inward and can never escape, white hole is a region where matter erupts outward and nothing can ever enter. If you imagine space-time as a flexible rubber sheet, a black hole creates a deep, inescapable pit, while a white hole forms an impossible, repulsive mountain that launches everything away. Both are valid solutions to Einstein's field equations. Yet, only one seems to exist in our observable universe. The physics of white holes defies common sense in ways that make even black holes seem simple. Picture standing at the edge of a white hole's event horizon. Unlike a black hole, where you could cross the boundary and fall inward, a white hole's event horizon acts as an impenetrable barrier. You cannot enter because matter and energy are constantly streaming outward at the speed of light. It would be like trying to swim up a waterfall that flows at an infinite speed. From the outside, a white hole would appear as the brightest object imaginable, a blazing sphere that continuously creates matter and energy, seemingly from nothing. The matter emerges from the central singularity, already moving faster than light, then slows down as it crosses the event horizon into normal space-time. This creates an expanding shell of material that carries enormous amounts of energy. But here is where white holes become truly strange. According to relativity, time flows differently near massive objects. At a black hole's event horizon, time appears to stop for outside observers. At a white hole's event horizon, time would appear to flow backwards. An outside observer watching a white hole would see matter emerging in reverse chronological order. The last particles to leave the singularity would appear first, and the first particles would appear last. This temporal weirdness might explain why we do not see white holes in our current universe. They may only be able to exist at specific moments in cosmic history, when the universe has the right conditions to support such exotic objects. Some physicists argue that white holes are fundamentally unstable, that any small perturbation would cause them to collapse or explode. Others suggest that they exist but are hidden behind their own event horizons, making them invisible to outside observers. But the mathematics of relativity reveals something even more remarkable. The interior of a black hole and the interior of a white hole are actually the same region of space-time. They are two different ways of looking at the same underlying geometry. A traveler falling into a black hole would, from their own perspective, eventually emerge from a white hole in another region of space-time, possibly in another universe entirely. This theoretical connection suggests that black holes and white holes always come in pairs, connected by what are known as Einstein-Rosen bridges, or wormholes. Matter that falls into a black hole in one universe might emerge from a white hole in another. If this is true, then our Big Bang could be the white hole exit of a massive black hole somewhere else. But the evidence for this connection goes deeper than mathematics alone. Deep in the equations of general relativity lies a shocking possibility that most physicists prefer to ignore. Every black hole in our universe might be connected to a white hole in another universe through an Einstein-Rosen bridge, a tunnel through space-time itself. This means that every star that collapses into a black hole, every particle that crosses an event horizon, might not be destroyed at all. Instead, it could be transported to another realm of existence and expelled through a white hole, creating matter and energy in a completely different cosmos. The mathematics work with terrifying precision. When you trace the geometry of a black hole's interior, the equations naturally extend into another, separate region of space-time. This new region has all the properties of a white hole, matter and energy emerging from a central singularity, an event horizon that nothing can cross inward, and a direct connection to our universe through the black hole's core. The two objects share the same interior space-time, but they have opposite orientations in time. Consider what this means for cosmic evolution. In our universe, massive stars collapse into black holes when they run out of nuclear fuel. The matter that falls into these black holes does not simply disappear. It gets funneled through the fabric of space-time to emerge in another universe. That other universe would see a continuous creation of matter and energy, appearing as white holes scattered throughout their cosmos. Meanwhile, if the stars in their universe collapse into black holes, the matter would tunnel back to create white holes in our own universe. This creates a cosmic recycling system of staggering implications. Matter is never truly created or destroyed. It simply moves between parallel universes through these space-time tunnels. Each universe feeds the other, with black holes serving as the exits and white holes serving as the entrances. The total amount of matter and energy across all connected universes remains constant, but it can flow freely between them. But here is where the theory becomes deeply unsettling. If this process has been happening throughout cosmic history, then most of the matter in our universe might not have originated here at all. The atoms in your body, the stars in the sky, the planets orbiting distant suns, all of it could be recycled material from forgotten civilizations and long-dead worlds in other universes. We might be living in a cosmic graveyard, built from the remnants of countless other realities. The implications extend even further. If white holes are creating matter in our universe, then we should be able to detect them. They would appear as objects that continuously generate energy without any visible source of fuel. They would shine with the light of creation itself, powered by matter falling into black holes in distant, unseen universes. Some astronomers have even suggested that certain mysterious, highly energetic objects in our cosmos, like quasars or gamma-ray bursts, might actually be evidence of white holes operating in our own universe. The connection becomes even more profound when we consider the Big Bang itself. If our entire universe began as a single, massive white hole, then everything we see around us emerged from a black hole in another reality. The evidence for this cosmic connection is hiding in plain sight. The most ancient light in our universe carries a secret message about its violent birth. The cosmic microwave background radiation fills every cubic centimeter of space with the leftover heat from when our universe first became transparent to light. About 380,000 years after the Big Bang, this radiation appears almost perfectly uniform in all directions, with tiny variations that seeded the formation of galaxies and stars. But hidden within this ancient glow are patterns that suggest something far more extraordinary than a simple explosion from nothing. The temperature of this background radiation is exactly 2.725 Kelvin above absolute zero, cold enough to freeze any known substance solid. This represents the cooled remnant of what was once the hottest plasma imaginable, with temperatures exceeding billions of degrees. As the universe expanded, this plasma stretched and cooled, like the exhaust from a cosmic engine gradually losing its heat. The mathematical signature of this cooling process matches perfectly with what we would expect from a white hole that has been expanding and cooling for nearly 14 billion years. But the real evidence lies in the uniformity itself. The cosmic microwave background is so evenly distributed that regions of space separated by billions of light years have exactly the same temperature. This presents what cosmologists call the horizon problem. How did these distant regions of the universe coordinate to reach the same temperature when they have never been in causal contact with each other? Light has not had enough time since the Big Bang to travel between these regions and equalize their temperatures. The standard solution to this problem involves a period of cosmic inflation, a brief moment when space itself expanded faster than the speed of light. stretching tiny quantum fluctuations into cosmic-sized temperature variations. But this theory requires exotic physics and a level of precise fine-tuning that many scientists find unsatisfying. The white hole hypothesis offers a much simpler and more elegant explanation. If our Big Bang was actually a white hole, then the uniform temperature makes perfect sense. All the matter and energy in our universe emerged from the same source, a single white hole connected to a single black hole in another universe. If all of this material originated from the same interior region of a black hole, then it would naturally have started with the same temperature and density. As this material emerged through the white hole, it carried the thermal signature of its origin. The slight variations in temperature that we observe today would represent the last moments of whatever fell into the parent black hole, different stars, planets, and perhaps even civilizations, each contributing their unique thermal signatures to the mix. Even more intriguingly, the cosmic microwave background contains unexpected patterns, known as anomalies, that do not fit the standard Big Bang models. There are mysterious cold spots, preferred directions in the polarization of the light, and correlations across scales that should not exist. These features have puzzled cosmologists for decades, leading some to question whether our universe is truly homogeneous and isotropic, as has always been assumed. But if our universe emerged from a white hole, these anomalies might represent the geometry of the parent black hole and the universe that created it. The patterns could be fossils, ancient imprints of the cosmic structure that existed before our own reality began. The evidence for this becomes even stronger when we examine the largest structures in our own universe. Something invisible and unimaginably massive is dragging our own galaxy, and thousands of others, toward it at 600 kilometers per second. This cosmic anomaly, known as the Great Attractor, lies hidden behind the dust and stars of our own Milky Way, making it nearly impossible to observe directly. But its gravitational influence is undeniable. It pulls on thousands of galaxies across hundreds of millions of light years. Including our own local group, this cosmic traffic jam defies our understanding of how matter should be distributed in a universe that began with the Big Bang. The mystery deepens when we realize that the Great Attractor itself is being pulled towards something even larger and more mysterious. Astronomers have mapped the flow of galaxies across billions of light years and discovered that everything seems to be moving toward a region of space called the Shapley supercluster. But even this massive collection of galaxy clusters cannot fully account for the observed motion. Something else must be out there. Something so massive that it dominates the gravitational field across significant portions of the observable universe. The standard model of cosmology struggles to explain how such large-scale structures could have formed from the smooth, uniform initial conditions of the Big Bang. But if our universe began as a white hole, these mysterious attractors make perfect sense. A white hole would not create matter uniformly in all directions. It would have preferred axes and orientations, determined by the geometry of the parent black hole. The matter emerging from different parts of the white hole's event horizon would carry momentum in specific directions, creating large-scale flows that would persist for billions of years. Think of it like water emerging from a complexly shaped nozzle. The pattern of the flow depends on the shape and orientation of the nozzle, not just the pressure of the water behind it. Similarly, a white hole would imprint the geometry of its parent black hole onto the matter it creates. If that parent black hole was rotating, had powerful magnetic fields, or was distorted by nearby massive objects, these features would show up as preferred directions and large-scale flows in the resulting universe. The Great Attractor and similar structures could be the fossilized remnants of this original white hole geometry. They represent the grain of our universe, The underlying pattern that was established when everything we see emerged from a single, directed point source. This would explain why galaxy flows seem to converge on specific regions rather than spreading out randomly in all directions. As the standard Big Bang model predicts, recent observations have revealed an even more disturbing possibility. The Great Attractor appears to be part of an enormous structure called the Laniakea supercluster, a sheet of galaxies stretching across more than 500 million light-years. This cosmic wall is so large that light has not had enough time since the Big Bang to cross it, meaning its different parts should not be gravitationally connected. Yet somehow, this massive structure exists and influences the motion of matter across vast distances. If our universe is the product of a white hole, then structures like this Great Wall might represent the last major features that fell into the parent black hole just before our universe began. The implications of this cosmic connection reach far beyond our own cosmic neighborhood. The missing mass that appears to hold our universe together might not be made of exotic particles at all. Dark matter makes up 85% of all matter in the universe. Yet, it interacts with ordinary matter only through the force of gravity. It does not emit, absorb, or reflect light, making it completely invisible to all of our telescopes and detectors. Scientists have spent decades searching for dark matter particles in deep underground laboratories, in powerful particle accelerators, and in space-based observatories. But every single experiment has come up empty. The persistent absence of evidence is becoming increasingly difficult to ignore. But what if dark matter is not made of particles we have never discovered? What if it represents something far stranger, the gravitational influence of matter that exists in the parent universe, connected to our white hole Big Bang? The mathematics of Einstein-Rosen bridges suggest that gravitational fields can leak through the theoretical tunnel, connecting a black hole to its white hole counterpart. This means that we might be feeling the gravitational pull of objects that exist in another universe entirely. Consider the implications. Every galaxy in our universe appears to be embedded in a massive halo of dark matter that provides the gravitational scaffolding for star formation and holds the galaxy together. These halos have specific shapes and densities that our computer simulations have been able to model remarkably well. But if dark matter consists of ordinary matter in another universe, then these halos would represent the gravitational shadows of the galaxy clusters surrounding the black holes that feed our white hole cosmos. The evidence for this fits with disturbing precision. Dark matter halos are most massive around the largest galaxies, exactly as we would expect if they represent the gravitational influence of the most massive black holes in the parent universe. The distribution of dark matter throughout our cosmos follows the same large-scale structure as ordinary matter, suggesting they share a common origin. Even the observed ratio of dark matter to ordinary matter, about 5:1, matches what we might expect from the inefficiency of matter transfer through an Einstein-Rosen bridge. This theory would explain why dark matter particles have never been detected, despite decades of dedicated searching. They do not exist in our universe at all. They are regular atoms, stars, and planets in another reality, whose gravitational fields reach across the dimensional divide. We are literally feeling the weight of another cosmos pressing down on our own space-time through the network of wormholes that connects every black hole to its white hole partner. The theory also explains dark matter's strange behavior during galaxy collisions. When two galaxies crash together, their stars and gas interact through powerful electromagnetic forces. But their dark matter halos appear to pass through each other with minimal interaction. This makes perfect sense if dark matter represents the gravitational shadows from another universe. The shadows can overlap without affecting each other, because they originate from completely separate objects in separate realities. Even more remarkably, this interpretation of dark matter provides a testable prediction for the white hole Big Bang hypothesis. If dark matter comes from gravitational leakage through wormholes, then its distribution should correlate with the locations of black holes in our own universe. Regions with more black holes should show stronger dark matter signals, and the orientation of dark matter halos should align with the preferred directions established by our universe's white hole origin. The connection between these two realities may run even deeper than gravity alone. The spookiest phenomenon in all of physics might be the ultimate proof that our universe shares quantum information with others. Quantum entanglement allows two or more particles to maintain instantaneous connections across any distance. Sharing information faster than the speed of light could travel between them. When scientists measure the spin of one entangled particle, its partner immediately adopts the opposite spin, regardless of whether they are separated by a few meters or by millions of light years. Einstein famously called this spooky action at a distance, because it seems to violate the fundamental principle that nothing can travel faster than the speed of light. But what if these entangled particles are not communicating across space at all? What if they are sharing information through the same Einstein-Rosen bridges that connect black holes to white holes? The mathematics of wormholes suggests that quantum information could flow through these space-time tunnels without violating the principles of relativity, because the information would not be traveling through our normal, three-dimensional space. It would be taking a shortcut through a higher dimension. This possibility becomes even more intriguing when we consider the origin of entangled particles in our universe. If our Big Bang was actually a white hole, then every particle that emerged from it would carry the quantum information from whatever fell into the parent black hole. Particles that were entangled in the original universe would remain entangled after passing through the wormhole, creating quantum connections that span the dimensional divide. Think about what this means for the nature of reality. Every quantum measurement we make in our universe might be influenced by events that are happening in the parent universe. When we observe a particle's spin or position, we are not just measuring properties that exist independently in our own reality. We are accessing information that is simultaneously stored in another cosmos. The apparent randomness that seems to govern the world of quantum mechanics might actually be a reflection of the chaotic dynamics of matter falling into the black holes in the parent universe. Recent experiments in quantum mechanics have revealed phenomena that seem to support this interpretation. Quantum teleportation, for example, allows scientists to transfer the complete quantum state of one particle to another, destroying the original in the process. The information appears to travel instantaneously, but it requires a classical communication channel to complete the transfer. This matches exactly what we would expect if the quantum information flows through a wormhole, while the classical information must travel through normal space-time. Even more remarkably, some physicists have proposed that the interior of every black hole contains a complete copy of all the quantum information that has ever fallen into it, stored on the two-dimensional surface of the event horizon in a kind of hologram. If this is true, then the white hole that created our universe would contain a complete quantum record of everything that existed in the parent cosmos. Our entire reality might be a three-dimensional projection of information that is stored on the surface of a black hole in another universe. This so-called holographic principle would explain why entanglement appears to connect particles across vast distances. They are not actually separated in the way we perceive them. They are both reflections of the same underlying information, stored on the event horizon of the parent black hole. When we measure one particle, we are simply accessing the same quantum record that determines the properties of its entangled partner. The implications of this extend beyond individual particles to the very structure of space-time itself. Everything you see, touch, and experience might be a projection from the surface of a black hole. The holographic principle suggests that all the information contained within any three-dimensional region of space can be encoded on the two-dimensional boundary of that region. Much like a three-dimensional image can be projected from a two-dimensional surface. This radical idea originally emerged from the study of black holes, where physicists discovered that the amount of information a black hole can contain depends on the area of its event horizon, not the volume of its interior. The implications are staggering. Our three-dimensional universe might actually be information that is stored on a two-dimensional surface. If our Big Bang was a white hole connected to a black hole in another universe, then our entire cosmos could be a holographic projection of the information encoded on that black hole's event horizon. Every atom, every star, every galaxy would be a three-dimensional shadow cast by patterns of information on a distant, two-dimensional surface. We would not just be living inside a projection. We would ourselves be a part of the projection. Conscious patterns of information experiencing the illusion of three-dimensional existence. The evidence for this bizarre interpretation comes from the mathematical structure of general relativity itself. When physicists trace the geometry inside a black hole, they find that all possible paths eventually lead to the same central singularity. But viewed from the outside, an observer watching matter fall into a black hole would see it appear to freeze at the event horizon. Its information spread across the surface in a holographic encoding. Both perspectives are equally valid mathematical descriptions of the same physical system. This duality extends to our own universe, from our perspective inside the cosmos. We experience a three-dimensional space expanding from a Big Bang singularity. But from the perspective of observers in the parent universe, our entire reality might appear as information patterns evolving on the surface of their black hole. The expansion of our universe would correspond to information spreading across the event horizon as more matter falls in from their side. The holographic principle would explain several puzzling features of our cosmos. Why does the cosmic microwave background radiation appear to come from a two-dimensional surface that surrounds us? Because it represents the projection of information from the black hole's event horizon. Why do the laws of physics in our universe seem to be so perfectly calibrated to allow for the existence of complex structures like stars, planets, and life? Because they reflect the information processing capabilities of the holographic encoding system. Even more disturbing is what this would mean for our concepts of free will and consciousness. If we are holographic projections, then our thoughts, our decisions, and our experiences might be determined by information patterns evolving on a two-dimensional surface in another universe. Every choice we think we make, freely, could be the result of quantum fluctuations in the parent black hole's event horizon. Our sense of agency and self-determination might be elaborate illusions created by the holographic projection process. But the holographic principle also offers a strange kind of hope. If information cannot be destroyed, even when it falls into a black hole, then consciousness itself might be a fundamental and indestructible aspect of the cosmos. Death might not be the end, but simply a transition from one form of information encoding to another. The connections between these universes may be more intimate than we ever imagined. Every black hole in our universe is slowly, imperceptibly evaporating. And when they die, entire universes might die with them. Stephen Hawking discovered that black holes are not completely black. They emit a faint glow of radiation due to quantum effects that occur near their event horizons. This so-called Hawking radiation carries away energy, causing the black holes to gradually shrink and, eventually, evaporate completely. The smaller the black hole, the faster it radiates away its mass. Stellar mass black holes will take longer than the current age of the universe to evaporate. But microscopic black holes would disappear in mere fractions of a second, releasing their entire mass as a final, brilliant burst of pure energy. But if black holes are connected to white holes in other universes, what happens when a black hole evaporates? The Einstein-Rosen bridge that connects it to its white hole partner would collapse, severing the link between the two realities. From our perspective, any white holes in our universe that were connected to evaporating black holes in another reality would suddenly stop producing matter and energy. They would appear to shut off, like cosmic faucets being turned off one by one. The implications are terrifying. If our entire universe emerged from a single white hole that is connected to a single black hole in another cosmos, then the fate of our reality is inextricably linked to the fate of that parent black hole. Should it ever evaporate completely, the flow of matter and energy that powers our cosmic expansion would cease. Our universe would begin to collapse back on itself, reversing the Big Bang and crushing everything we know back into a singularity. The timeline for this cosmic death depends on the mass of the parent black hole. If it was formed from the collapse of a single, massive star, it would evaporate in about 10 to the 67th power years, an unimaginably long time, but still finite. If it was a supermassive black hole, like those found at the centers of galaxies, it could survive for 10 to the 100th power years, or even longer. But eventually, unless the parent black hole continues to grow by consuming new matter from its own universe, it will shrink to nothing and take our universe with it. This creates a disturbing symbiosis between connected universes. Our universe needs the parent black hole to survive, but that black hole needs matter falling into it from the parent universe to avoid evaporating. If the parent universe goes through its own heat death and stops feeding matter to its black holes, then our universe, and countless others, would be doomed as well. We are living in a cosmic ecosystem where the death of one universe can cascade to cause the death of others. But Hawking radiation also offers a strange glimmer of hope. The radiation that is emitted by a black hole carries with it information about everything that has ever fallen into it. If our universe is connected to a black hole through a white hole, then the information that defines our cosmos might be encoded in the Hawking radiation that is emanating from the parent black hole. Even if our universe is ultimately destroyed when the parent black hole evaporates, the information that defines our reality would persist as a faint thermal radiation in the parent cosmos. This raises profound questions about the nature of existence and consciousness. If the information that makes us who we are can survive in the form of Hawking radiation, are we truly dead when our universe ends? The answer to that question may lie in understanding how black holes form in the first place. Every time a massive star dies in our universe, it might be giving birth to a new cosmos. When a star at least 25 times more massive than our sun runs out of its nuclear fuel, the force of gravity overcomes all other forces and crushes the star's core into a black hole in less than a second. The outer layers of the star explode outward in a spectacular supernova that can briefly outshine an entire galaxy, while the core collapses past the point of no return. What happens next has been hidden behind the veil of the event horizon, since Einstein first predicted the existence of black holes nearly a century ago. But if black holes are connected to white holes in other universes, then this stellar collapse is not an ending, but a beginning. The matter that is crushed into the black hole does not simply disappear. It emerges as a new Big Bang in another reality. Every supernova we see in our night sky might be marking the birth of trillions of galaxies, countless stars, and potentially countless new civilizations in universes that we will never be able to see. The death of one massive star could seed an entire cosmos with the building blocks of complexity and life. This idea transforms our understanding of cosmic evolution. Instead of being a random, improbable accident in an indifferent universe, life might be an inevitable consequence of the cycle of stellar death and rebirth. The heavy elements that make up our bodies, the carbon, the nitrogen, the oxygen, and the iron were all forged in the fiery cores of dying stars and scattered throughout space by supernovae. If those same elements then go on to seed new universes through the formation of black holes, life becomes a kind of cosmic inheritance, passed down from one generation of universes to the next. The process might even be self-reinforcing. Universes that produce many massive stars would, in turn, create many black holes, spawning many child universes. Those child universes would inherit the physical constants and initial conditions that are favorable for star formation, making them more likely to produce their own generations of stellar offspring. Over vast cosmic timescales, the multiverse would evolve toward configurations that maximize the production of complexity, structure, and potentially consciousness. But the collapse of massive stars into black holes is not the only way that new universes might be born. Theoretical physics suggests that microscopic black holes could form during extremely high-energy particle collisions, either naturally, in the interactions of cosmic rays, or artificially, in our most powerful particle accelerators. If these tiny, fleeting black holes also connect to white holes in other realities, then every cosmic ray shower and every high-energy experiment we conduct might be creating miniature universes that expand to cosmic proportions in their own separate spacetimes. This possibility carries with it profound implications for our responsibility as an intelligent species. If our own scientific experiments can create entire universes, then we may bear a moral responsibility for the realities that we bring into existence. Every time we collide particles at high energies, we might be playing God with the fate of countless future civilizations. The decisions we make about how to conduct high-energy physics could determine whether these child universes develop in ways that support or prohibit the emergence of consciousness. The connection between stellar death and cosmic birth suggests that our own universe exists within a vast, interconnected genealogy of realities. Each one spawned from the collapsed remnants of massive stars in its parent cosmos. But this raises some disturbing questions about our own cosmic ancestry. If our universe was born from a white hole, then somewhere, in another reality, a civilization may have watched as their own star system was consumed by a black hole. The very matter that makes up our entire cosmos, every galaxy, every star, every planet, and every living being might once have existed as a thriving civilization in another universe. Their sun could have been a massive star, approaching the end of its life, growing unstable as the nuclear fuel ran low in its core. They might have been an advanced civilization, capable of recognizing the signs: the increasing stellar output, the irregular flares, and the inexorable expansion that signals a star's transition towards a supernova. Perhaps they tried to escape. An advanced civilization facing the collapse of their star might have attempted to evacuate their entire star system, loading their population onto massive generation ships bound for the distant stars. But if their sun was destined to become a black hole, any escape might have been impossible. The gravitational effects would have begun long before the final collapse. disrupting the orbits of their planets and making interstellar travel increasingly difficult. They might have watched helplessly as their own world was pulled apart by the immense tidal forces, knowing that their entire reality was about to disappear forever behind an event horizon. The final moments of their existence would have been indescribable. As their planet crossed the black hole's event horizon, time would have appeared to slow to a crawl from the perspective of any outside observers. But for the dying civilization, time would have continued to flow normally as they fell inexorably toward the central singularity. They would have experienced the ultimate fate of all matter that enters a black hole spaghettification, where the extreme gravitational tidal forces stretch objects into long, thin shapes like spaghetti. But according to the white hole hypothesis, their death was not the end. The very information that defined their civilization, the quantum states of every atom in their bodies, the molecular structures of their DNA, the complex neural patterns that encoded their memories and their consciousness, all of it would have been preserved and transmitted through the Einstein-Rosen bridge connecting their black hole to our white hole Big Bang. This means that we might be living in the expanded, cooled remnants of their reality. The very atoms in our own bodies could be the same atoms that once formed their bodies. The carbon in our DNA might have once stored their genetic information. The iron in our blood could have once flowed through their veins. We would be their resurrection, their continuation in a new form, within a new cosmos. The implications of this extend beyond individual atoms to the largest structures in our universe. The distribution of galaxies in our cosmos might be a reflection of the distribution of matter in their original star system. The faint patterns in our cosmic microwave background could carry the imprints of the temperatures of their planets. Even the fundamental laws of physics in our universe might be influenced by the physical conditions that existed in their reality just before their black hole formed. This creates a profound and deeply personal connection across the dimensional divide. We might share a common heritage with beings that we will never be able to meet, carrying forward their legacy in ways they could never have imagined. Our universe would be their afterlife, a continuation of their existence in a form so transformed that they could never recognize it. But if this is true, then our own ultimate fate might already be determined by the evolution of the massive stars in our own cosmos. The massive stars that are burning in our night sky today will ultimately determine whether our own universe has a future. Our cosmos contains billions of massive stars that will, one day, collapse into black holes. Each one of these represents a potential birth event for a new universe. But they also represent a gradual, inexorable drain of matter and energy from our own reality. As these stars reach the end of their lives and their matter crosses their own event horizons, they will carry with them portions of our universe into other realities. Over vast cosmic timescales, this process will strip away the raw materials that are needed for continued star formation and cosmic evolution. The timeline is both vast and finite. Most of the massive stars that are currently burning will become black holes within the next few billion years. Our own sun, while not massive enough to form a black hole, will expand into a red giant and eventually shed its outer layers as a planetary nebula, leaving behind a white dwarf that will slowly cool over trillions of years. The last red dwarf stars will continue to burn for hundreds of trillions of years, but eventually, they too will exhaust their fuel and fade away. As fewer and fewer new stars form, our universe will enter what cosmologists call the degenerate era. The only remaining light will come from the slow cooling of white dwarfs, the occasional flash from a neutron star, and the rare burst of energy when a wandering object falls into a black hole. But even this dim illumination will eventually fade as the white dwarfs cool to match the frigid temperature of the cosmic microwave background. After 10 to the 37th power years, protons themselves may begin to decay, dissolving the very atomic nuclei that form the foundation of matter. But if our universe is connected to others through a network of black holes and white holes, this so-called heat death might not be the final end. Every black hole in our cosmos is connected to a white hole somewhere else, potentially in universes that are much younger and more energetic than our own. As our universe grows cold and dark, these connections might provide pathways for energy and information to flow back into our reality. The black holes themselves will become the dominant features of our dying cosmos as they slowly evaporate through the process of Hawking radiation. They will release their stored energy back into space, potentially providing the last source of power for any civilizations that manage to survive the heat death. But this process will take an unimaginably long time. Stellar mass black holes will require 10 to the 67th power years to evaporate completely, while supermassive black holes could persist for 10 to the 100th power years, or even longer. During this incredibly long twilight period, the connections between universes, through the Einstein-Rosen bridges, might become more important than the physics that operates within any single cosmos. Advanced civilizations might learn to harness these connections, using them to move between universes or to draw energy from younger, more vigorous realities. The multiverse would become a vast network of interconnected worlds with matter, energy, and information flowing through the wormholes that link dying universes to newborn ones. In this scenario, our universe would not truly die, but would instead merge gradually with the larger community of connected realities. The very boundary between one cosmos and another would begin to blur as matter and energy flow freely through the network of wormholes that connects every black hole to its white hole partner. But this raises a chilling question about whether we have any control over our own cosmic destiny. We might be living inside a vast, interconnected network of universes, each one feeding matter and energy to the others. If every black hole is connected to a white hole in another universe, then the multiverse forms an intricate and complex web of interconnected realities. Matter that falls into a black hole in universe A emerges from a white hole in universe B. Stars that collapse in universe B feed black holes that, in turn, create white holes in universe C. This process could continue indefinitely, creating a cosmic ecosystem where no energy is ever truly lost. It simply moves from one reality to another through the Einstein-Rosen bridges that thread through a higher dimensional space. This cosmic ecosystem would have its own evolutionary dynamics. Universes that produce many massive stars would, in turn, create many black holes, generating numerous connections to other realities. These highly connected universes would become the hubs in the multiverse network, receiving matter and energy from many different sources while simultaneously feeding multiple child universes. Over time, the multiverse would develop a complex topology, with some universes serving as major nodes and others existing as isolated, peripheral branches. The flow of matter between these universes would not be random. The amount and type of material that emerges from each white hole would depend on what falls into its connected black hole. A universe whose parent black hole consumes mostly primordial hydrogen and helium would start with simple initial conditions that are favorable for the formation of stars. But a universe that is born from a black hole that swallowed an advanced technological civilization might inherit exotic matter, artificial elements, or even information-rich structures that could accelerate the development of complexity within it. This creates the disturbing possibility that some universes are being deliberately cultivated by advanced civilizations in their parent realities. A sufficiently advanced species might be able to control what falls into their own black holes, essentially engineering the initial conditions for the child universes they create. They could seed new realities with the building blocks for life, for technology, or even for consciousness itself. We might be living in a cosmic garden, carefully tended by beings that we will never be able to meet. The ecosystem model also provides a natural explanation for why the fundamental constants of physics in our universe seem to be so perfectly tuned for the existence of stars, planets, and life. If universes that produce interesting and complex structures are more likely to spawn child universes with similar properties, then the multiverse would naturally evolve toward configurations that support complexity. The anthropic principle. The observation that our universe seems to be uniquely designed for our own existence would be a natural consequence of this cosmic selection pressure, rather than a miraculous coincidence. But ecosystems can also experience catastrophic collapses if the flow of matter between universes becomes disrupted. Entire regions of the multiverse could experience cascading failures. A universe that suddenly stops receiving matter from its parent black holes would begin to collapse as its expansion energy dissipates. This collapse could, in turn, trigger the formation of new black holes, potentially creating a feedback loop that spreads the destruction to other, connected realities. The stability of our own universe might depend on the health of the entire multiverse ecosystem. We are not isolated observers in a single cosmos, but active participants in a vast community of interconnected realities, each one dependent on the others for its continued existence. Understanding this profound connection becomes crucial when we consider what might lie beyond our own cosmic horizon. The edge of everything we can see might be hiding the definitive evidence of our white hole origin. Our observable universe extends for 46.5 billion light-years in all directions, encompassing everything from which light has had time to reach us since the Big Bang. But this represents only a tiny fraction of the total universe, which might extend infinitely in all directions or might have a boundary that we cannot yet detect. Beyond our cosmic horizon lies a realm that will remain forever hidden from our telescopes and instruments. Yet, it might hold the key to understanding our true cosmic nature. If our universe began as a white hole, then the region beyond our observable horizon might still show direct evidence of this origin, while we see only the cooled, uniform remnants of the initial explosion in our own local region. The true edges of our universe might still be experiencing the active creation of matter from the original white hole source. These distant regions could be blazing with the energy of continuous creation, far brighter and more energetic than anything we observe in our local cosmic neighborhood. The mathematics of white hole formation suggest that matter would not emerge uniformly in all directions. Instead, it would follow preferred axes, determined by the rotation and magnetic field structure of the parent black hole. This means that our universe might have a grain, a fundamental asymmetry that points back toward the original white hole source. The cosmic microwave background radiation already shows tantalizing hints of such asymmetries, with temperature variations that seem to align along specific directions in space. These anomalies become more significant when we consider that our observable universe might be biased toward the calmer, more uniform regions of a much larger white hole explosion. We could be living in the cosmic equivalent of a quiet eddy, while the main torrent of creation continues to rage beyond our horizon, the mysterious, dark flow. The observation that galaxy clusters throughout our observable universe seem to be moving in the same inexplicable direction might represent the gravitational pull from the edge of this torrent, tugging on the matter that is within our observational reach. Even more intriguingly, the boundary of our observable universe might not represent a smooth transition to the unobservable regions. If our cosmos emerged from a white hole, there could be sharp discontinuities where different phases of the explosion created regions with dramatically different properties. Beyond our horizon might lie domains where the laws of physics take on different forms, where the fundamental constants have different values, or where matter and energy exist in exotic states that we cannot even imagine. Recent observations have revealed structures in our own universe that appear to be too large to have formed through gravitational collapse since the Big Bang. The Hercules Corona Borealis Great Wall of Galaxies stretches across distances so vast that light has not had time to cross them. Yet somehow, these massive structures exist and show signs of gravitational organization. If our universe extends far beyond what we can observe, these impossible structures might represent the edges of the original white hole explosion, fossilized boundaries where different phases of matter creation overlapped and interfered with each other. The true scale of our universe might dwarf our current understanding by factors of millions or even billions. We could be microscopic observers in a cosmic explosion that continues to unfold across distances we cannot possibly comprehend. This possibility becomes even more profound when we consider our own place in cosmic history. Intelligence might be the universe's way of understanding its own white hole origin. Throughout cosmic history, our universe has evolved from simple hydrogen and helium into increasingly complex structures. Stars, planets, molecules, and eventually, life itself. This seemingly inexorable progression toward complexity appears to violate the second law of thermodynamics, which states that entropy, or disorder, should always increase over time, making systems more disordered rather than more organized. Yet, here we are, conscious beings capable of contemplating our own existence and the nature of reality itself. If our universe emerged from a white hole that is connected to a black hole in another reality, then consciousness might represent something far more significant than an accidental byproduct of chemical evolution. The very information that fell into the parent black hole would have included whatever conscious beings existed in that previous reality. Their thoughts, their memories, and their collective knowledge would be encoded in the quantum states of the matter that emerged from our Big Bang white hole. This means that consciousness might be a fundamental feature of our universe, not an emergent property that arose billions of years after the initial explosion. The potential for awareness, for intelligence, and for self-reflection could be built into the very fabric of space-time, waiting for the right conditions to manifest itself in biological or perhaps technological forms. We might be the universe becoming conscious of itself, literally reliving the thoughts and experiences of beings who died in black holes eons ago. The implications of this extend beyond individual consciousness to our collective intelligence. As our civilization develops more sophisticated technologies for processing and sharing information, we might be unconsciously reconstructing knowledge that originally existed in the parent universe. Our scientific discoveries could, in fact, be rediscoveries. Our technological innovations could be reinventions. And our deepest philosophical insights could be ancient wisdom, finding new expression through different minds in a different reality. This interpretation would explain why mathematics seems to describe the physical reality of our universe with such uncanny and mysterious precision. The mathematical relationships that we discover might not be the abstract constructions of human intellect, but literal information patterns that we have inherited from the parent universe. The very equations that govern quantum mechanics, relativity, and thermodynamics could be the fossilized memories of how physics worked in the reality that preceded our own. Even more remarkably, our own growing understanding of black holes, of white holes, and of the connections between universes might represent the universe developing the capability to understand its own origin. Through our scientific investigation, we are gradually reconstructing the story of how our own reality came to exist. We are becoming conscious of our own cosmic ancestry in ways that might parallel how the parent civilization became conscious of their own origins before falling into the black hole that ultimately created us. This creates a profound and inescapable responsibility. If consciousness represents the universe's attempt to understand itself, then every act of discovery, every moment of insight, and every expansion of our collective knowledge contributes to a cosmic awakening that may span multiple realities. We are not just passive observers, trying to make sense of an indifferent universe. We are active participants in the universe's own journey towards self-awareness. But this also raises some disturbing questions about the nature of our own free will and our individual identity. If our thoughts and our discoveries are somehow predetermined by information that we have inherited from another reality, do we truly have any agency? Or are we simply playing out pre-established patterns, established by minds that died billions of years ago? The answer to that question might determine whether consciousness has a future beyond our own current cosmic epoch. The white hole hypothesis creates paradoxes that challenge our very understanding of cause and effect across multiple universes. If our universe was born from a white hole that is connected to a black hole in another reality, then time itself becomes deeply problematic. Einstein's theory of relativity shows that time flows at different rates in strong gravitational fields. It slows down near massive objects and can even appear to stop entirely at the event horizons of black holes. But for objects that are actually falling into a black hole, time would continue to flow normally from their own perspective. This means that the civilization that fell into our parent black hole might still be experiencing their final, terrifying moments, even though billions of years have passed in our universe. From our perspective, their death was instantaneous and occurred at the very moment of our Big Bang. But from their perspective, they might still be falling toward the central singularity, their time stretched out across what we perceive as the entire history of our own cosmos. This creates a temporal paradox, where the same event, their destruction and our creation, is occurring simultaneously across completely different timescales in different realities. The paradox deepens when we consider what happens when the massive stars in our own universe collapse into black holes. If these black holes are connected to white holes that create new universes, then we are continuously spawning new realities that might, one day, develop their own civilizations. But the effects of time dilation mean that the civilizations that are falling into our own black holes might be experiencing their own deaths across timescales that span the entire future history of the universes they create. This suggests that all of these connected universes might exist in a complex temporal web, where cause and effect operate across multiple times simultaneously. The death of a star in our universe creates a new Big Bang in another reality. But from the perspective of the matter that is falling into our black holes, that Big Bang might not occur until our own universe has evolved for trillions of years. The future of these child universes becomes entangled with the present of their parents in ways that violate our normal, linear understanding of causality. Even more disturbing is the possibility of closed time-like curves existing within this multiverse network. If Universe A creates Universe B through a black hole connection, and Universe B eventually creates Universe C, what happens if Universe C somehow connects back to Universe A? This would create a causal loop, where each universe is simultaneously the parent and the child of the others. The very Big Bang that created our reality might be the result of black holes that will form in our own distant future. These temporal paradoxes might explain some of the mysterious fine-tuning that we observe in our universe's physical constants. If our cosmos exists within a causal loop, then the very parameters that govern its physics might be self-consistently determined by the requirement that the universe must be capable of creating the black holes that will, in turn, give birth to itself. The anthropic principle would become a kind of bootstrapping mechanism, where the universe literally pulls itself into existence through its own future evolution. But these closed time-like curves also raise profound and unsettling questions about free will and determinism. If our universe is locked into a causal loop with its own future, then every choice we make might be predetermined by the requirement that our cosmos must evolve in exactly the way that is needed to create the black holes that birthed us. The implications of this reach far beyond physics and into the very realm of existence itself. If our universe was born from a white hole, what created the universe that created the black hole that created us? The white hole hypothesis solves the problem of how something can come from nothing by suggesting that our Big Bang was not a true beginning, but simply a transfer of matter and energy from another reality. But this explanation simply pushes the ultimate question back one level. Where did that parent universe come from? If it also emerged from a white hole that was connected to a black hole in yet another reality, then we are faced with an infinite regression of universes creating universes, without ever reaching a true, ultimate origin. This infinite chain of cosmic ancestry creates profound philosophical problems. Each universe in the sequence requires a previous universe to explain its own existence. But the sequence as a whole has no beginning and no ultimate cause. We find ourselves in the middle of an infinite causal chain, with no way to determine whether there was ever a first universe, or whether the multiverse has always existed in some form. The mathematics of general relativity offer several possible resolutions to this paradox. One possibility is that the sequence of universes eventually loops back on itself, creating a closed causal structure where Universe A creates Universe B, which creates Universe C, which, eventually, creates Universe A again. In this scenario, the entire multiverse would be self-creating, with no external cause needed to explain its existence. Each universe would be both the effect of previous universes and the cause of future ones. Another possibility is that the infinite regression is real, but that the sequence converges on some fundamental set of physical laws and initial conditions, just as an infinite series of numbers can converge on a finite sum. An infinite sequence of universe-creating events might converge on a stable multiverse structure. The ultimate reality would be this convergent limit, rather than any individual universe within the sequence. But perhaps the most disturbing possibility is that this infinite regression reveals something fundamental about the nature of existence itself. Reality might not require an ultimate cause or a first principle. Instead, it might be an eternal, self-sustaining process, where every level of description depends on deeper levels, without ever reaching a final foundation. We would be living in a universe that is built on an infinite tower of explanations, each one requiring the next, without ever reaching a solid bedrock. This interpretation challenges our deepest intuitions about causality and explanation. We are accustomed to thinking that every effect must have a cause, that every explanation must rest on more fundamental principles, and that every chain of reasoning must eventually reach some basic axioms or first principles. But the white hole multiverse suggests that reality might be more like a self-referential loop than a hierarchical structure with firm foundations. The infinite regression problem also has profound implications for the meaning and purpose of existence. If our universe is just one link in an endless chain of realities, each one creating the next, without any ultimate goal or destination, then the question of why anything exists at all might be meaningless. The multiverse would simply exist because it exists, with no deeper reason or purpose beyond its own self-perpetuation. Yet, even in the face of this infinite regression, there might be patterns and purposes that emerge at higher levels of organization, giving meaning to individual universes and to the conscious beings that exist within them. Our exploration of this cosmic hierarchy brings us to the ultimate question about our own place within it. We might be living at the most crucial and significant moment in our universe's history, the point where it develops the ability to understand and, potentially, control its own cosmic destiny. If our universe did, in fact, emerge from a white hole, then we are the first generation of conscious beings that are capable of discovering this profound truth. Throughout the billions of years since our own Big Bang, matter has organized itself into increasingly complex and sophisticated structures. But only now has it reached a level of complexity that is needed to contemplate its own origins. We stand at a unique and powerful threshold in the history of cosmic evolution. The very moment when the universe becomes aware of its own nature and begins to take conscious control of its own development. This newfound awareness brings with it an unprecedented level of responsibility. Previous generations of life on our planet could evolve and go extinct without affecting the fundamental structure of reality. But we are now developing technologies that could, one day, allow us to manipulate space-time itself. Our particle accelerators might be capable of creating microscopic black holes. Our experiments with quantum mechanics could allow us to exploit the connections that may exist between universes. And our theoretical frameworks might eventually allow us to engineer the very physical constants that govern our reality. If consciousness is the universe's way of understanding itself, then we are on the leading edge of a cosmic awakening that could transform the entire multiverse. Our scientific discoveries are not just academic exercises. They are active interventions in the universe's own self-development. Every time we probe deeper into the nature of reality, we change the universe's understanding of itself, potentially altering its future evolution in ways that we can barely begin to imagine. The white hole hypothesis suggests that this process has been happening throughout the multiverse for eons. Each universe that develops conscious life contributes to a collective understanding that flows through the network of black hole and white hole connections. The knowledge that is gained by civilizations in the parent universes might influence the physical laws and initial conditions of their child universes, creating a form of cosmic inheritance that becomes more sophisticated with each passing generation. We might be approaching the point where this inheritance becomes conscious and deliberate. Advanced civilizations might eventually learn how to control what falls into their own black holes, effectively programming the initial conditions for new universes. They could seed these new child realities with specific arrangements of matter and energy that are designed to accelerate the development of complexity, of intelligence, and of consciousness itself. The multiverse would transition from a process of random cosmic evolution to one of intelligent design on the largest possible scale. But this immense power comes with an ultimate moral responsibility. If we can influence the development of child universes, then we must grapple with questions of cosmic ethics that no previous generation has ever had to face. What kind of initial conditions should we create for these new realities? Should we optimize them for the rapid development of intelligence, for the minimization of suffering, or for the maximum possible diversity of experiences? Every decision we make about high-energy physics could affect the fate of countless future civilizations. The white hole hypothesis transforms our understanding of humanity's cosmic significance. We are not meaningless accidents in an indifferent universe, but active participants in the multiverse's own journey towards self-awareness and self-determination. Our species might be remembered not for our individual achievements on this small planet, but for our role in the moment when the cosmos first became conscious of its own nature and began to shape its own destiny. The universe is becoming aware of itself through us. And what we do with that awareness might determine the future of reality itself. We began this journey by asking whether the Big Bang was, in fact, the first white hole. And we have discovered something far more profound. The evidence points toward a cosmos that is far stranger and more interconnected than we ever could have imagined. A multiverse where black holes and white holes form the bridges between different realities, where matter and energy flow freely between universes, and where consciousness itself might be the universe's own method of understanding its own nature. Our Big Bang was not the beginning of everything, but a single, momentous event in an infinite network of connected realities, each one born from the death of massive stars in their parent universes. This revelation transforms our understanding of existence itself. We are not isolated observers in a single cosmos, but active participants in a vast community of interconnected realities. The very atoms in our bodies have journeyed across dimensional boundaries, carrying with them the legacy of civilizations that may have died in black holes billions of years ago. The galaxies that we see in our night sky are arranged according to patterns that were established by the geometry of our parent black hole. Even our thoughts and our discoveries might be the echoes of knowledge that originally existed in another universe entirely. But perhaps most remarkably, we find ourselves at the very threshold of a cosmic awakening. For the first time in our universe's history, matter has organized itself into forms that are capable of understanding their own origins and, potentially, controlling their own destiny. We are the universe becoming conscious of itself, developing the ability to shape the multiverse through our own scientific discoveries and our technological capabilities. This awareness brings with it both hope and responsibility. If we can learn to harness the connections that may exist between universes, we might be able to transcend the limitations of our single cosmos and tap into the vast resources of the multiverse network. Death might not be an ending, but simply a transition to new forms of existence in other realities. The ultimate heat death of our own universe might be avoided by learning to draw energy from younger, more vigorous universes that are connected to us through these Einstein-Rosen bridges. Yet, we also face unprecedented moral challenges. If our own high-energy experiments can create new universes, then we bear a profound responsibility for the countless civilizations that might one day develop in those realities. If consciousness represents the multiverse's own journey towards self-awareness, then every act of our discovery contributes to a cosmic awakening that could transform the very nature of existence itself. The white hole hypothesis suggests that we live in a universe where nothing is wasted and nothing is ever truly lost. Matter and energy flow between realities in an eternal dance of creation and destruction. Consciousness emerges wherever the conditions allow, carrying forward the accumulated wisdom of countless previous civilizations. The multiverse evolves toward ever greater complexity, intelligence, and self-understanding through the actions of beings like ourselves. Our universe may have been born from a white hole, but that is not the end of the story. It is barely the beginning. We are a part of something that is infinitely larger than ourselves. Yet, our own individual choices and our collective discoveries contribute to the multiverse's ongoing evolution. The cosmos is not just our home. It is our collaborator in the greatest adventure of all the universe's own quest to understand itself. And what we do next might determine whether that quest succeeds or fails.